So hi, welcome to EpiCentre seminar series again. I'm Jun, and it's our third presentation. So today's speaker is Dr. Hamed, and Hamed is a mathematician and who joined EpiCentre this year as a postdoctoral fellow. His presentation today will be about the research experience of mathematical modeling to examine the impact of different control options for dengue fever. Hamed, please.
Hello, good day, everyone. Thank you for making your way to my presentation. So today I will briefly talk about our previous work on the transmission dynamics of dengue fever. So dengue is currently one of the most common arbovirus infection worldwide. And according to the CDC, about 400 million people get infected with dengue annually. So, and the spread of dengue is through this bite of an infected Aedes mosquitoes. So the transmission cycle is that when the Aedes mosquito bites an infected human, then the mosquito now, if it bites susceptible woman, so this leads to the transmission of dengue. And there are 4 different strains of dengue fever, which is the dengue 1 up to dengue 4. And there are 3 spectrums of dengue. So the first one, which is classified as the primary infection, which is the dengue fever itself. And we have the secondary infections, which are the dengue hemorrhagic fever and the dengue shock syndrome. Where is dengue found? So dengue risk area. So this map here shows the risk area across the world where dengue is being found and where it is being endemic. So from the map, we can see the white regions. These are the risk free areas where they are free of dengue presently, and the yellow one is where it is very low, and the red one is the high risk. So presently we can see New Zealand belongs to the white region, meaning that New Zealand is dengue free at present. So it is commonly found in the tropical and subtropical regions of the world. So today I will be talking about the mathematical modeling of dengue fever. So in our model, we considered the population of human population and mosquito population. So this human population is classified into 5 epidemiological subclasses, where we have SH, which is the susceptible woman, EH, that is the exposed, A is the asymptotic woman, while I is the symptomatic. Symptomatic. A is asymptomatic, and I is the symptomatic, which is also infectious class. Then we have the RH, which is the recovery class. For the mosquito population, we have the susceptible mosquito and the exposed mosquito, which is the EV, and IV, which is the infected mosquito. So in this compartment diagram, so the dashed red line corresponds to the interaction between human and mosquito population, which leads to the spread of the disease. So in doing that, we formulate a mathematical model, which are 8 in number, depending on the depending on the class where we have SH, like I've mentioned, to be the susceptible woman, up to IV, which is the infected mosquitoes. So, and some of them, all other terms here, apart from the epidemiological classes, so all other ones are the model parameters. For example, the lambda H here is the recruitment rate of human, while the lambda V, which is this one, is the recruitment of the mosquito. We have the biting rate as well. So I will not want to waste more time on this. So I will quickly talk about the qualitative analysis of the dengue model itself. So the first thing we look at is the existence of equilibria. So that is the steady state of the model itself. So the first one is the dengue-free equilibrium, which is also known as the disease-free equilibrium. So for the disease-free equilibrium, we set the derivative of our model to 0. So in that case, we have this EF, which represents the dengue-free equilibrium. So SH, which is the susceptible, and SV, which is the susceptible vectors. As we know, in the dengue-free, the infected classes are zeros. So that is why for EH up to IH, RH here are zeros, and same thing for the EV and IV. And we have lambda H over mu H to be the disease-free equilibrium for the susceptible human class, and this term here for the susceptible mosquito class. So in order to further our analysis, we looked at the RT, which is the control reproduction number, which is also known as the effective reproduction number, and denoted by RT in this case here. So what does RT mean? RT is just the invasion threshold threshold for predicting dengue outbreaks, and also evaluating the control strategy that would reduce the spread of the disease. So that is just simple illustration or explanation of what RT is. So the other equilibrium that we look into is the dengue present equilibrium, which is also known as the endemic equilibrium. So in this case, for the endemic equilibrium, the infected classes, that is both exposed, the asymptomatic and the infected class are greater than 0. Same thing for the mosquitoes. So in short, we represent EP as the dengue present equilibrium and EF as the dengue-free equilibrium. So what we need to know here is that if our RT, which is the control reproduction number, if it is less than 1, then we say that our dengue-free equilibrium is globally asymptotically stable. Otherwise, it is unstable. Also, if it is greater than 1, then we have our endemic equilibrium, which is the dengue present equilibrium, is globally asymptotically stable. Otherwise, it is also unstable. So in the subsequent slide, I'm going to show the through my some plots to show the asymptotically stability of the disease-free and the endemic equilibrium. So before we look at that, before we look at the global stability of our equilibria, so we consider bifurcation analysis that exists in our model. So what does bifurcation analysis mean is that we want to look at how varying different parameters affect the dynamics of the model. So in this case here, we consider varying our R0, which is the basic reproduction number, where against the force of infection, that is the human force of infection of human, which is the lambda H. So from here, in this plot here, we have this blue line corresponds to the stable disease-free equilibrium, while the red dashed line corresponds to unstable disease-free equilibrium. While the magenta one here, the dashed magenta corresponds to the stable endemic equilibrium. So from here, if our R0 is greater than 1, we see that we have our endemic equilibrium, which is stable, and for R0 less than 1, it is we have disease-free to be stable. Now that we have established the existence of forward bifurcation analysis in our system, so we tend to now look at the stability analysis of both the disease-free equilibrium and the endemic equilibrium. So the plot here corresponds to different initial sizes for the infected class for human and mosquito class. So as we see, irrespective of initial size of the exposed human, the solution tends to the disease-free equilibrium for the all classes. The same thing here, if you look at the asymptomatic class, they all go to the disease-free equilibrium. Same thing for the mosquito class, that is the exposed and the infected classes of our mosquito. So this is showing that our disease-free equilibrium is globally stable. Then also for the disease present equilibrium, dengue present equilibrium, which I've called the endemic equilibrium. Also, if irrespective of the initial classes that we've considered, we see that they all goes to the disease present equilibrium, that is the endemic equilibrium. So this is the case of the exposed human. So meaning that the dengue will always establish itself in the community or in the population. Now, so another analysis that we checked or we looked into is the sensitivity analysis. So the sensitivity analysis is almost similar to bifurcation analysis, but in this case, the approach is different. So here we look at how each of the parameter varies or changes with respect to the control reproductive number, which is the RC. So this is just the formula that is being used to check for the sensitivity index for each of the parameter which are present in the RT terms, which I've shown in the previous slide. So here, looking at this, we see that the sensitivity index for the biting rate is 1, which means that if biting rate is increased by 1%, that leads to increase in the spread of the disease. And looking at this one here, which is the lambda H, that lambda H, which is the recruitment of the susceptible woman. So we can say that the sensitivity index here is negative, meaning that if this is being reduced by 0%, and 0.5, which is like 50%, means that the transmission of this disease will also reduce. So same thing for transmission probability and the recruitment rate of the vector. So this is just showing how each of these parameters are significant in our model. So what other thing is the partial rank correlation coefficient? So this is also a sensitivity analysis, but this is based on statistical algorithm, which is the Monte Carlo algorithm. So looking at this plot here, we can see the larger rectangles shows the rectangles shows how significant each of the model parameter affect the dynamics of the model. So as we can see here, we see that the biting rate is to this end, the biting rate is almost 0.5, which corresponds to 1% that we see in the parameter sensitivity index, meaning that the biting rate of the mosquito and the death rate of the mosquito are more significant in our model, meaning that if the mosquito is being reduced in the population, that results to decrease in the spread, or that reduces the spread of dengue in the population. And also looking at this one, which is the biting rate, if the mosquito is present in the population and the biting rate is high, it means that that results to increase in the spread of the the dengue in the population. So the other thing that we looked into, because what I've explained in the previous model, the model is non-optimal control model. So now we looked into optimal control model. So for the optimal control model, we modify the non-optimal control model by introducing different control strategies. So, and the control strategies are modeled as a time-dependent functions. So the first one is what we call UP, which is the control using the insecticide treated bed net or mosquito repellent lotion. So the UE, that corresponds to the treatment of the exposed individual using drug therapy. We have the UI, which is the treatment of the symptomatic infectious individual, and UA, which is the use of the adulticide, or which is also the open spray, the spray of insecticide across the environment. So we solved our model using the Pontryagin maximum principle by considering the objective functions. So in our objective function, we've included all these these 4 control strategies in the model. And in order to check the effect or the impact of different strategy in the model in the dengue transmission, so we consider combination of different strategies, so which we've called strategy A up to strategy E. So for the strategy A, we use all the 4 control interventions, that is UP up to UA, that is the insecticide treated bed net, or up to the use of the adulticide. For the control strategy B, we only consider, for other strategies, we only consider the use of combination of 3 different strategies. So in the next slide, I'm going to show the effect of the impact of each of these strategies on the dengue transmission. So for this one here, this is the control intervention using strategy A, which include all the 4 control interventions. So looking at this plot here, this is the case of the exposed human. So the blue curve corresponds to the case where the intervention hasn't been introduced into the model, while the dashed red curve corresponds to when we have introduced the intervention. So as you can see that without the intervention, the disease persists in the optimal control problem. But when we introduce all the 4 strategies, that diminishes the spread of the dengue fever, dengue in the population. This is also observed in other subclasses for the human subclasses and the vector subclasses itself. So this plot here, this is the control profile plot for the strategy A. So looking at this the dash curve here, this corresponds to the intervention using the insecticide treated bed net. So we can see the duration of the simulation is up to 250 days. We can see that from this control profile, this indicates that the insecticide bed net should be consistent should be in the lower band, which is a 0 lower band, until around 180 days of our simulation time, which it needs to be introduced up to 100%, which will be used 100% to be you should be used maximally until around 220 days, which whereby it goes back to the lower band. But for the for the UE, which is the treatment drug therapy for the exposed case, and UI for the infectious class, and we can see that they are also in the lower band until around 220 days, which goes to around 0.1, which is like 19% here. Then it goes back to the lower band again after around 220 days. So then, and looking at the green curve here, which is the control intervention with the use of the agdoticide, you can see that this shows that it should be used maximally from day one of the simulation until last day of the simulation. So for the strategy B, we also use the same thing, but in the strategy B, we only have the use of the insecticide treated bed net and the use of the chemotherapy for the asymptomatic and the symptomatic population without the agdoticide. So looking at that, we can see that the effect of this strategy, we can reduce the infected exposed human population towards the end of the simulation, like the last 5 days. Same thing for the asymptomatic human and the infected human, and also for the exposed vector, which is the exposed mosquito. And we can see for the infected mosquito, there is no significant effect of this strategy on the infected mosquito. And that is also observed in the control profile here in the figure F here. So similar dynamics is observed in other control strategy, that is from strategy C up to strategy E. The dynamics is similar to the one that is observed in strategy A. That is, when we include this the strategy, there is a reduction in the transmission of the dengue fever in the population. So now we later consider the cost effectiveness analysis because we've used different strategy. So for the cost effectiveness analysis, we want to check which of these different strategy is effective and it is also least costly. So in order to do that, we used the incremental cost effectiveness ratio, which is known as ISA. So, and this is calculated using this this formula here, that is looking at the change in the total cost over change in the cost control benefit for different strategy. So what this ISA does is that we compare two different strategies and check the one with the lower ISA, the least ISA value. So from the table here, we can see we have different strategies. So NS corresponds to where there is no strategy being applied in the model, while we have the strategy B up to strategy E. So the total infection averted for each of the strategies is what is listed here. We see that for strategy D and up to strategy E, they have the same total infections averted apart from strategy B. And this column here corresponds to the total cost for each of the strategy. So applying the ISA formula here, we first compare strategy B with when there is no strategy. So the ISA value is this in the last column here. Also, we compared strategy D and strategy B, and we've got this ISA value here. So the dashed line, the dash value here, the reason why we never consider the ISA for the case of C with D or A to D is because they are having the same total infections averted. So in that case, but looking at the total cost, we see that strategy D is having the least cost here, meaning that strategy D is cheaper and more effective than any of the strategies that we've considered in this is cheaper and the most effective compared to all other control interventions that we have considered. Now I would like to make short comment in in terms of the implication of dengue fever for this the disease-free area. So I'm going to use New Zealand as a case study, as we have seen that New Zealand is also free of dengue. So looking at this figure here, this is the reported notifiable cases of dengue fever between 2000 and 2009 of dengue fever in New Zealand. This is from the ESR page. So as we can see, we see that the cases are increasing, as we can see from the trend line here. So this has been what scientists have been talking about, that how the risk of New Zealand being prone to dengue fever. So there have been a lot of experimental research and observation to see if there are vectors that can result in dengue being coming into New Zealand. So, and one other thing is that there are different factors that can lead to this, and one of it is as a result of climate change. So, due to temperature increasing annually. So, this is one of the studies that was done recently, looking at the increment. I'm looking at how the temperature changes, and they also predicted that the temperature will continue to increase until you can say up to year 2100. So meaning that if as the temperature increases, that could be if the environment is conducive for the mosquito to survive in the environment, this is a risk of dengue coming into New Zealand or any other dengue-free areas. So, and it has been shown that it has been explained or seen that the up north of New Zealand, the upper north of New Zealand, has a warm subtropical climate. So, and in summary, in this presentation, I've described the dynamics of dengue transmission using a mathematical model, and also established the existence of disease-free and endemic equilibrium, and also showed through bifurcation analysis that there is forward bifurcation, meaning that the dengue transmission can be controlled in the population, irrespective of what is being observed in the model. And as well, we also use optimal control analysis to explore different impact of different control strategy on the spread of the disease. And for the future work is to check to look at the impact of climate variability on dengue transmission. So as it has been studied and shown that seasonal effects also take account into the variation of spread of the disease. So we we aim to look at the effect of climate change using surveillance data to check how the disease can be affected or can be spread through these factors, that is the temperature, the rainfall, and humidity. And lastly, I would like to acknowledge the people who I've worked with, that is Afis Abidemi, who is a lecturer at the Federal University of Technology, Accra in Nigeria, and this other two, Joseph and Joshua, in Kwame Nkrumah University in Ghana. And thank you all for your attention.
Okay, great. Thank you, Hamed, for your presentation, and thank you all of you to join today's meeting seminar. So we are heading to the December now, and as you all may know, this is kind of now vacation season is starting in New Zealand. So our next seminar will be during February next year. And until then, see you guys. Bye-bye. Thank you for joining us again.
Thank you.